Hi, my name is Paulo Castro, and in this session, we're going to talk about best practices for Azure Search. I work on the Azure Search team, and as part of our engineering work, we work with a lot of customers to make sure they get the best out of the service. And in this session, what I wanted to do is walk through some of the best practices we've learned in the context of Azure Search, particularly around scalability and performance. So let's get started by getting a big picture of all the building blocks that are there in Azure. You can see Search kind of playing a role there. And today, I'm also going to use some of the other building blocks to put together end-to-end solutions that involve Search, but also help us build scalable, highly available solutions for Search. So in terms of the plan for this session, I'll briefly introduce Search in a few minutes, and I'll give you pointers to more details in case you're not familiar with Azure Search. And then I'll talk about performance and scale for specific search services at first. And then I'm going to take it one step further and talk about indexing and searching beyond single services for scenarios where you either need global availability or you have a very, very large footprint that you want to manage around search. So first, let me briefly put Azure Search in context. So if you use any application that is heavy on content, in this case, I'm just speaking on Yelp, you'll see that we are all used to these search experiences that have very interesting building blocks. You expect of these sites great search, including keyword search with smart linguistics. We all also used to things like suggestions. We all do this. We start typing and kind of wait a little bit to see what pops. We all expect filters. If the application runs on a device, like an example in the screenshot here, then you expect geo-location awareness. So all these parts make up a great search experience. And Azure Search brings all these building blocks together into a service that is ready to go, that you can just push your data in and then consume without having to become an expert in maintaining search service, like from the infrastructure perspective, or an expert in search itself, like linguistics and ranking and so on. If you want to know more about the introduction aspects of Azure Search, I included some links here to a good write-up, also to some videos from previous conferences, and to very detailed videos of step-by-step all the aspects of search that you can go watch online. In addition to, at the end, I have some pointers on how to contact us and engage with us if you have questions or if you're using Search and you want to see if you're using it the best way possible. So with the context out of the way, let's talk about performance and scale for Search. In the context of full-text search, performance is important in a couple of aspects. One is we're all used to Bing and Google, where as soon as we type something, we expect instantaneous responses, great ranking, solid linguistics, and so on. And when we add search to our own applications, our users expect the same from them as well. So we want to make sure we have that experience out. We've also seen many applications our customers build that not only use Azure Search as their search backend, but also they run the bulk of their online presence off of it. Let's say the backend for their mobile application or maybe their website, because all the data is already there, and it's a very quick data source to use for serving content out to customers. So when approaching performance, the first thing or the first principle to bear in mind is, what are you trying to achieve? We see a lot of cases where we sit down with customers and discuss the kinds of performance needs that they have. And the first thing folks do is they grab some sort of performance testing tool and they hammer the service with everything they have. And the thing is certainly at some point you squeeze the thing out of capacity, but often you would not learn much from that exercise. What you want to do when it comes to performance tuning is first pick the things that you know. Typically, the first thing you know is the kinds of queries or searches that your application will do. And the other thing you'll often know is what is your target latency. Are your users in the scenario that you have willing to wait, say, 100 milliseconds, maybe 500 milliseconds, a couple of seconds for big searches or big results? So depending on that, you know what kind of capacity you want to start with and what experience you want to construct. Once you have a target latency, then what you want to do is create a target data set and then increase the load on the data set. And as you increase the load, more and more queries per second, then you'll see that latency will start to slow down once you're getting close to using all the capacity that you provisioned. At that point, you know how many queries per second you can handle with the capacity that you have. So now there's another data point that you may or may not have. If you know how many queries per second you need to serve, then it's a question of adjusting the capacity of the service until you can hit that many queries per second with your target latency. If you don't know, then you can still do the exercise of starting with the target latency until it starts to drift a little bit, and then increase the capacity of the service that you provisioned, and then push again, and then increase again, and push again. And that way you have a map of, for each click stop in the different capacity options that you have in Azure Search, how much QPS, how many queries per second can you get at your target latency. That way, you're not just maxing out the service just for the point of maxing it out, but rather you're getting a good sense of how much capacity can you get, how much latency you get as a result of that. There's many ways to do that. If we look at Visual Studio here, one tool I like a lot that is built into Visual Studio is the web load testing tools. They run on your computer on agents, or they run as a cloud service as well. So it's really convenient, even if you have to do very large scale testing. And usually you split this in two. So here you can see I have a simple test. And they already provide all the building blocks to construct the test and execute it, in this case, an HTTP request. And you can see I have a few services here. We'll use them in a minute. You can construct, in this case, a search call. So once you have a search service up and running, like here I have one where I indexed all of Wikipedia. You can give us like an API version, a search string, a few options, and then execute the request. And then you can ask Visual Studio to execute lots of these in parallel and kind of turn it into a load and performance test. When it comes to testing for search, you want to make sure that you're testing on your target data set or a data set of similar distribution. You also want to make sure that if you're going to have overlapping search and indexing workloads, then you have them during your test. And also change with varying input. If you always search for the same keywords, that gets caught in all the caches and intermediate layers in the system. So you're not testing the real user experience. For example, what I did here is I wrote a little program to sample a bunch of titles and extract words from it. So now I have a Word file. And then whenever I run an instance or an iteration of the test, you can see here that I'm producing a string of as many terms as I want. That is just a concatenation of a set of random words. That way, I don't have a test that is running on the same words all the time. It's all over the place. So it's really exercising the functionality of the index. And then when you're ready to run it, what you can do is you can create a load test, and you can parameterize a bunch of things like the test mix and whatnot. And then you can create a load pattern. In this case, for example, this is simulating just 10 users. This is where I was saying we see sometimes folks saying, well, let's just put as many as we can. This is not going to quite teach you much. But what you can do is increase in steps to see what is a balance point where you can still have your latency but get the most out of the capacity you provisioned. Turns out that Visual Studio and the load testing machinery can do that as well. There is a load pattern called a goal-based load pattern. If you look at that one, what you can do is you can say which measure to track. In this case, we're measuring how much time it takes to do one test, so effectively the latency. And then you can give a minimum and a maximum edge, and then how much to increase on each iteration. So what the system will do is it will increase the load more and more until it goes past the minimum point, which in this case is the minimum latency, and it will stay between the minimum and the maximum latency. So that way, you can get a nice chart of how many queries per second you can get while staying within your margin of latency, whatever it is for your particular scenario. All right, so that's in terms of the approach for performance testing. Now, once you start tuning this, what you'll need to do likely is to scale the service. In many cases, a default single unit instance will do well, particularly for testing. But even in production, maybe it's just add a replica for high availability, but it'll do really well. But in other cases, when you have more requests, then you'll want to understand how to scale the service. So when scaling Azure Search services, what you do is you have two variables to dial, partitions and replicas. So replicas, think of it as copies of the data. So these are multiple instances of all the resources that back the search service, such that when you're running many queries, we can spread them over all these replicas evenly and effectively get more queries per second. Since there are multiple copies, it also means there's more availability. So if one of them go down, not the whole thing goes down. Partitions, on the other hand, think of it as also units of capacity, resources, that are used to host slices of the data. So the more partitions you have, the more data you can host, because each slice is autonomous and contains a maximum amount of data. If you need more, you add another partition and you have twice. If you need more, you keep adding, and so on. There is also the other effect where partitions, since they are independent of each other, for some cases, you get more parallelism out of them. And I'll drill into some examples of that in a minute. If you look at the Azure portal here, what you'll see is, let me open a service that I already created. This is a service that, as I mentioned before, has English Wikipedia loaded in it. You can see it has about 12 million documents. And in this particular case, what I have is 6 partitions and 1 replica for it. And if you need to change this, you can move these 2 dials to change the number of partitions or the number of replicas. This is an online operation, meaning you can do it while you're taking a workload. It'll slow down a little bit while we're reshuffling the data, but then you'll get the new capacity once we're done. So once you've experimented with this, you can start asking the question of what is the right scale for my particular service. So a few key questions to ask is, do I need more replicas, more partitions, or both? If your data simply doesn't fit in a particular data service, then you need to keep adding partitions until it fits, of course. Now, once you have a search service that has the data and it fits it appropriately, you still have to ask, if I want more performance, what do I do? So the first question is, are individual queries fast enough? If they are, then that means that maybe even if you don't have partitions, a single unit of search will get the request and will be fast enough to compute the answer and then give it to you. If you find that a single request is fast enough, but then you have so many requests per second that they become slow, latency goes too high, then what happens is you're just running out of resources in that unit, and what you want is more replicas, more copies of that. On the other hand, if individual queries are not fast enough, what happens there often is that the cost of computing the results of the search request you're formulating is too high. So you can use partitions as a way to split the data. Since you're splitting the data, you're also splitting the computation. So you get a kind of a MapReduce effect, where you get more parallelism in computing the results, and then you get that back to the client. Once you reach the point where individual queries go fast enough, then you can increase the number of replicas until you hit the right level of concurrent queries per second. Let me show you a couple of examples of this here. So this is a generic HTTP client that I'm using just to hit our API directly. And let me start with a query. So search people say like a low recall query. So it's a query that has high selectivity, so it matches a few rows. These queries tend to be very quick. In this case, I'm sending my API key, my version, and then I'm saying my search is Roman Empire. Remember, this is Wikipedia. And then I have a few extra fields, like a random color and a random rating and so on. So in this case, I'm saying, and the random color is red. So I have 3 services that I kind of went over quickly before: AzureCon 1, 2, and 3. This one has lots of partitions in them. This one has a few replicas in them, and this is a single instance service. So when I send a query like this to number 1, this guy has 6 partitions, no replicas. So it does, it varies quite a bit, but it's in the 100 milliseconds ballpark. If I go to 3, which is the one that is a single unit, you'll see that actually it's not particularly faster. And the reason for this is there is not a lot of work to do here. This query is very selective, meaning once we find the keywords, we can isolate the results, and there's not a lot to rank either. So we can come back very quickly. And the only reason to add more replicas here would be if we have so many queries per second that we can't keep up with the latency. We have customers like this where they have many, many hundreds of queries every single second. So they run on 6 or sometimes even more than 6 replicas because they need that kind of parallelism. Let me take a different type of query. So this one has one key change. So when I indexed this instance of Wikipedia, I disabled the English analyzer. I used a generic analyzer that is not language aware. So that thing doesn't know that the word "the" it means it's a very generic word in English. So it doesn't know to treat it as a stop word. So it's all over the place. So now I'm asking for all the documents that have the word "the" in it. And if I hit number 3 with it, we'll see that it takes maybe 600-700 milliseconds to run, because you have to find all of these and then rank it. Let's go to number 1. Remember, this one has six partitions, 1 replica, but 6 partitions. So we can see that this takes kind of in the 250 milliseconds. So it's about 3 times faster. Of course, it's more expensive, but we are getting more capacity back. So this gives us the ability to pay for as much performance as we want. And the fact that we can partition it out means we can get the right latency. And then if we have more queries per second, then again, we add partitions. Kind of an extreme example of this is, one of the things that makes the system do a lot of work is when you have low selectivity queries. That is, when you have queries that match many, many documents, because we have to at least rank them. And in some cases, when you use faceting, like here, facets are the hit counts per category, then we have to go compute the counts. So in this case, let me kick off this search request, where what I'm doing is there is no search string. So it matches all 12 or so million documents that I have. And then it has facets by authors and color and whatnot. And it also does order by a geodistance, which is, instead of ranking, we have to sort by these distance computations. It's quite a bit of work. And we see it takes about 3, almost 4 seconds to run. And we see kind of the results here. We see the facets are very big, like authors, like this guy has this many edits, this guy has this many edits. It's also interesting that all the top authors seem to be bots. And then at the end, we get the actual results of kind of things that matched. So if we switch to number 1, the one with 6 replicas, and we run the same search request, you'll see that it takes often like about a second or maybe a little less. So more than 3 times faster than the other one. And this is because we get parallelism out of splitting out. So a key question here is, first, how fast a single query is. Based on that, you know the level of parallelism you need. And then once you're done with that, then you can add replicas to get more queries per second. Just to rehash a little bit, key drivers for latency. First of all, low selectivity. If you have queries that match nearly all your data set, then those things are slow, particularly if you have a complicated sorting criteria or if you have a complicated ranking profile. I'm not going to talk a lot about scoring today, but we allow you to create custom scoring profiles to control exactly how we score documents. And the more complicated those are, the more it takes us to compute them. Also, high cardinality fields give us a little bit of trouble. This is harder to demonstrate here. But the underlying problem is if you do things like filters or especially facets, and a particular field has a very broad domain, that is, it has a lot of values, then those are very memory intensive for our implementation. And if you have lots of them and you go back and forth, then we end up seeing a lot of cache churn under the covers. And you'll see that as a slowdown, which will result in higher latency. So whenever you don't get the latency you want, first 2 things to look at is high cardinality fields. Do you really need them? And low selectivity queries. Are you missing a good filter? Or should you do and instead of or with the keywords so that you get a quick response with a small data set that users can interact with quickly? Of course, overlapping index load can also consume a lot of resources. So you have to dial up or down how much concurrent loading you're doing with search, maybe depending on the time of the day, or maybe depending on characteristics of the load that you're aware of ahead of time. So one more note on scalability. So far, I talked about scalability in the context of performance and latency. From the availability standpoint, since replicas are effectively copies, the more replicas you have, the more guarantees of availability you have. You need at least 2 to get an SLA from us. And with 2, you get read availability. We may have periods of times where writes bounce, but reads will always be there up to the SLA. If you have at least 3 replicas, then you get read and write availability. You can get up to 12 replicas on a search service. And of course, the more replicas you have, if one goes down because of a glitch or maintenance or whatever, then the less capacity you lose, so the less you feel the impact of it. And you also, of course, get more queries per second. And also, of course, you pay more for the whole thing. OK, so far, we've talked about scalability and availability within a region. So what if you have so much load? Or what if you have such a distributed user base that you care about where in the world the users are sitting, and you want to do the best to get to them quickly and maybe scale to the point that is beyond what you can do within a single data center? We have 2 challenges for that: getting the data into the indexes and then serving the content. So let's say that the approach is we're going to create multiple search services in multiple regions. First, we need to index the content. You have in Azure Search, you have a couple of options for indexing content. You can push the content, or you can have as pull. For push, there is an API. It's very straightforward, just some HTTP, JSON in, JSON out. So you can run your indexing logic either in a central place or maybe replicated in multiple places. Web jobs are an instance of a tool that are great for doing this. You can use workers as well. And that it's up to you to handle the distribution. The one thing you should assume or be careful with is when you're pushing, you may push successfully to one index and not to the other for whatever reasons, like a network glitch or something. So don't assume that these things will move uniformly. Assume that independently you'll have to retry and make progress, and only in a convergent way you'll reach consistency across them. For the pull case, we have a tool called indexers. It works great on single services. You can just point us at the data source of the ones we support, and we'll just handle indexing for you. For this case where you have distributed indexing, it's even more convenient because you can have multiple indexers pointing at the same or different data sources and handle indexing for you. There's a couple of patterns for this. If you have a single data store and you don't need that data store to be distributed, then you can just have multiple indexers and all point at it and handle the indexing for you. And then since search is already distributed, then if your application runs off of search, it doesn't matter whether the store is available or not, or slow or fast, because maybe it's not used at runtime. In the other case, it may be that you already need your underlying store to be replicated. And in that case, you can run local indexers on each one of them. You'll get better latency, and also you get more isolated failure modes for each. Which one you use depends on, of course, the cost implications of this and whether you really need the store to be distributed. Let me show you a little bit of this. I'm going to start with the one where you have replicas of your underlying store. And for that, I'll just show you what it looks like. We're not going to go all the way on this one. In this case, I have a SQL database. SQL has a support for replication out of the box. So what you can do is when you have a SQL instance, you can go to the geo replication area, and you can literally, just in the map, click in the places where you want one or more replicas to exist. For this pattern to work, you need readable secondaries. So you need to enable this in the right edition. And once you have it, then SQL will do its own replication. And then for all you know, each one is an independent database, and you can just pull content from there. So it's very handy if you already replicate SQL because you need it for your application, for maybe the backend for your mobile app, or maybe it's just your website. The other alternative is maybe you want just one store. You just want all the pointers to point at it. So let me walk through an example of that. Here, I have a DocumentDB database. And what I'll do is I have two search services. And in this case, instead of the Wikipedia set, since I want to do it on the spot, I have a smaller data set. I took the sessions from our last event from Build. And I have two services. So let's take one of them. So one is in South US, and the other one is in Asia to simulate this dual region event. And we could have more than two. So what I'll do is I'll go to the Asia one that is not set up. And what we'll see here is this will come up in a second. And there are no indexes in this service. So what I'll do is I'll set up an index and an indexer all at once. So what I'll do is I'll say import data. And the first step is to connect to a data source. We support SQL and DocumentDB today. We're working on more, so you expect more data sources to be supported soon. In this case, I'll say DocumentDB. I'll call this build, give a connection string. We're making this a lot better. You'll be able to browse your own DocumentDB or SQL account soon. And then I'll use the sessions collection, hit OK. And when we do this, we can go inspect the store, get some metadata about the store, and then get a sense of what a reasonable index schema would look like. And we'll propose the schema as a starting point. In this case, I'm going to call this index sessions. And here are all the fields that we saw. So I'll say, well, we want all these guys to be retrievable so we can bring them down. Some of them we may want to filter on, like the tags and the speaker name, and maybe the start, and even the room. Some of them maybe are sortable, like the title and maybe the start time. Facets, which is the hit count. Maybe we'll do tags, speakers, and start time. And finally, searchable, we want the title, the abstract, and speaker name. So we know in which parts we do full text search. You can pick analyzers. This is if you want to enable a particular language. We support about 50 languages, and this is support for that. And suggesters allow you to configure type like autocomplete. So we build a different type of index that you can use to create an autocomplete experience. So we can create one by saying, for example, all the titles form the pool of options that we want to propose in autocomplete. Great. So now let's give the indexer a name. And now that we have all the data, what the system will do is we'll go off, create an index, then create a data source, an indexer, put the whole thing together, and then create the index and run the indexer for the first time. At that point, we'll have the data in the index, and later we can configure a schedule. So this runs periodically, the text changes, and maintains our index up to date. So we can see our index here, our new data source, and in a second, the indexer will run, and we'll be able to monitor it here. So if we do one of these per service, then each instance of the service will have its own indexer, and they will all pull from the same store. Like we can see here, this instance just succeeded. And if you have multiple of them, you can use this UI to manage and make sure manage them, make sure they're in good shape and they're succeeding. So going back to the deck, once we have this set up, we have distributed indexing. The next question is, now that we have all these indexes around the world, then how do we make good use of them in the context of search? So by the time you need something like this, usually you're past what a single service can do. Single services can handle a huge amount of queries per second. That said, there are a couple of scenarios where you want more than that. One is that you want geo-redundancy. The other one is that you want to have latency-optimized routing. So you get the quickest you can to the closest region to where the user is using your application, so you get the best experience. We have a component on Azure called Traffic Manager that is a great building block to achieve these types of scenarios. This may also be a case where you have many thousands of requests per second, more than what a single service may be able to handle in some cases. And so you would consolidate multiple of them around the world, and that's how you would partition your load. So from the architecture perspective, a good mix that works really well is you can combine search with a web app, either to render a website or to act as the backend of a mobile app, and Traffic Manager to create a front end that is a full stack. So what you do is you have your search backend, any other backend you might have, and the front end duplicated in multiple regions. And then you teach about the whole thing to Traffic Manager. So if any of the components go down, you want to make sure the whole thing is taken offline, and the other instances in other regions will take over. That way, if a region goes down, or even one component in a region goes down, your application continues to work. So let me show you this real quick. So coming back here, what I have in Visual Studio here is, let me run this so I can show you working, is a local version of, I just took the content I just indexed, and what I have is a trivial UI. So let's look for Azure Search. And what this does is just lists all the sessions and the information in them, and it has all the facets in them and so on. Like very simple but typical search interface. So if I want to have this be distributed, then first thing to do, which I already did and I can show you here, is deploy it in multiple regions. In this case, I deploy the website in 2 places, or the web app in 2 places, in East Asia and in South US. So I have 2 instances of this that I can access independently. So I can say AzureCon South US, and this is one instance, and the other one the same in Asia. So you can access them separately. But what I want to do is make them coordinated. So what I'll do is I'll put a Traffic Manager endpoint on front of them and teach it to go into one and the other. And I'll tell it to do it based on latency. And I'll walk you through this in a minute. The important thing is, not only we want to route based on latency, but if one is down, we want to take it to the other. And we want to make sure that it's not just if the website is down. What if the website is up, but the search components or some other component is down? We want to make sure Traffic Manager understands the entire stack so it knows that the whole thing is up. One way to do this is to have a probe, and Traffic Manager supports having one of these. So for example, here, in this app, this is the controller that backs the app we're just looking at. It's very simple. It just uses the Search API to issue a search request. So one way to wire this up is you can have an endpoint. In this case, I'm going to build a simple controller. We'll call it the ping controller. And all we want to do here is when somebody hits this endpoint, we want to say 200 if we're in good shape, or we want to fail if we're not in good shape. Even the website may be in good shape, but maybe the backend isn't. So for in the context of search, one way to do this is turn this into an async method. I'll just make a call to, I already set up, if you're using a dependency injection framework, this will look prettier than here. But I have the Search SDK installed, and I hooked up my client to my credentials, so I have it in a global. So I'm going to say documents.search. And actually, I'm not going to search for anything. I'll say null. And let's put it here. And I'm going to pass parameters. In particular, I'll say top 0, because I want to do as little work as possible here. All I want to do is I want to issue a search that checks all the way into the engine and back. So the empty search will do that. And then let's put a cancellation token here. Let's put the default one. So what this will do is, if the search service is healthy, then it'll just return from here. We don't actually care about the result. We can say response.status code is 200, and we're done. If search is down, then this guy will throw an exception, and things will go wrong. So let's see it here. So let me run the app. And if we go hit the ping endpoint, then this is succeeding. So this is going to be similar to the traffic manager endpoint that I have in acondemo.trafficmanager.net, where you can see I'm being routed at the South US one, and I can kind of search for something here. So what I'll do now to simulate a failure of this is I'm going to go to my search service in South US, and I'm going to stop it. So once the service stopped, it's going to stop responding. So my local ping endpoint will just start to fail like this. So now, what I'll do here is, let me ping real quick, use acondemo.trafficmanager.net. You'll see that, so this is the address that we were pinging under the covers. So let me do that to flash DNS, and let's give it a second. Let me show you how this is configured in Traffic Manager, and then show you how it fails over. So I have a Traffic Manager endpoint here. And you can see that I configured 2 endpoints. And the endpoints correspond to my 2 applications, to the 2 instances of web apps that I deployed. And I configured the endpoint so that it has a relatively short TTL. I overdid it here for the purpose of the demo. 30 seconds is too little. 300 seconds is, I think, is the default, more typical value. And I also told the system to ping the ping endpoint. So it's continuously pinging that to see if it is up. As long as it's up, then it routes based on latency. If one of them is down, then it removes that from the equation and randomly redirects you somewhere else, so that you always land on an endpoint that works. So after the TTL expires, and sometimes it takes a little time, so I'm not sure it'll be quick enough here, but we'll see. If we ping the same endpoint, we'll wait a little more. You'll see this change to the East Asia one, because basically Traffic Manager is resolving this DNS name into a different name that then goes into the different instance of your full stack, like your website and your backend as well. So after a few seconds after DNS expires everywhere, the new resolution will route you somewhere else. This way, on the healthy case, you get geo-distributed load, and in the case where some failure happens, your load automatically reroutes somewhere else. So this is a really powerful way to approach global redundancy, where you get very good scale, but you also get redundancy in case of failures of all sorts at any layer of the stack. In terms of resources, I've walked very quickly through some performance and scalability aspects of Azure Search. There are many aspects I didn't touch on. When you talk about search, ranking is a very interesting topic. Linguistics is very interesting, and there is more to it as well. So I've listed a lot of resources here. There's links in all of them. At the beginning of the deck, I also included my email address, my Twitter handle. Feel free to ping me through any of these channels or the rest of the team. We're always curious to see what people are doing with Azure Search and how can we make it better. So I hope you enjoyed this and have a good rest of the day.